Okay, I want you to just for a second picture the beginning of everything. The classic image of the Big Bang we've all seen.
Hmm.
You hit rewind on the universe, and all the galaxies fly backward, stars dissolve, everything gets hotter, denser, until you hit a wall.
The wall, yes. The single point where everything is squashed together. Infinite density, infinite heat.
A singularity. It's basically the ultimate do not enter sign in cosmology.
Mm.
The story always goes that at that moment, the laws of physics just break.
They wave a white flag, yeah.
Yeah.
The math completely falls apart. We call it the Planck scale problem.
Yeah.
Standard models assume that at time zero, conditions are so extreme that things like mass, temperature, even space-time,
Yeah.
they just lose their classical meaning.
You're trying to divide by zero,
Yeah.
basically. And usually the answer is, well, we just need to figure out quantum gravity to fix it. Some kind of magical new
Well,
physics.
we're waiting for a breakthrough, but what if
Yeah.
what if we're overthinking it?
What if we don't need new physics?
Exactly. And that's the question we're tackling today. We're looking at a fascinating paper by Reza Rezikonkha, and its title is pretty bold. The universe began as light, a classical alternative to Planck scale cosmology.
So the whole premise is,
Yeah.
forget the tiny broken speck of matter. What if it all started as just light?
Pure light. And the claim is, if you start from there, you can actually explain the universe's birth using classical physics, stuff we, already understand.
So classical electromagnetism, thermodynamics, that kind of thing.
That's the idea. The mission here is to build a classical bridge over that singularity using parameters we can actually measure, like energy density and volume, instead of just getting lost in quantum assumptions.
I love that. Trading infinite weirdness for something we can actually get our heads around. But to do that, the paper starts by, well, it takes a sledgehammer to one of the most famous equations in history.
Oh, it does. We have to talk about Einstein, specifically EMC22.
Energy equals mass times the speed of light squared. It's on T-shirts. How can that be a mistake?
It's not so much a mistake as checking the fine print. The equation is brilliant for converting mass into energy. But think about the very first instant of the universe. Time equals zero.
Okay, I'm trying to picture it.
In that pre-matter era, before any particles have formed, rest mass. The M is basically undefined.
Right, you can't have the mass of a particle if there are no particles yet. It's like trying to weigh a cake before you've even bought the flour.
Exactly. So if you use that M to calculate the energy of the baby universe, you're starting with a faulty assumption. The tool just doesn't fit the job.
So how does Cunny fix this? If we can't use mass, what do we use?
He goes back to basics. Classically, mass is just density times volume, m equals rho v.
Okay, a simple substitution.
So he just rewrites Einstein's equation. Instead of E mc22, it becomes var d v c22. Density times volume times c squared.
That seems like a small algebraic trick, but I have a feeling this changes everything.
It changes the entire perspective. By swapping mass for density and volume, we stop thinking about discrete particles, about things. We start modeling a continuous field of energy filling a space.
That feels much more fluid. We're not counting little rocks of matter. We're measuring a smooth sea of energy.
Precisely. And this lets us calculate energy continuously from time zero without needing mass to exist. But then you have the second variable there, volume.
Right. What's the volume of a brand new universe?
This is where the geometry comes in. The author just assumes the universe is a sphere, expanding at the speed of light. So the volume isn't static, it's a function of time.
So you start the clock, it expands outward at light speed, and the volume is just how much space that light has covered.
Correct. And when you plug that in, you get a model where energy evolves over time. It shifts the whole focus from a particle-based explosion to a field-based, evolution.
It's made of light. It's very elegant. But the paper takes another turn that I found really cool. It zooms right in on c, the speed of light itself.
This is one of the strongest parts of the paper, I think. We usually just treat c's as a number, a constant. But it's not arbitrary. It comes from somewhere.
From Maxwell's equation.
Yes, from James Clerk Maxwell. The speed of light is defined by the properties of the vacuum itself, two constants specifically: vacuum permittivity and vacuum permeability.
I always have trouble visualizing those.
Think of them as the stiffness of empty space. Permittivity is how much the vacuum resists an electric field, and permeability is how much it resists a magnetic field.
So C is just how fast a wave can travel across that fabric.
Exactly. And the math is CWO equals 1 over the square root of those two constants multiplied together. So Kankha takes that definition and plugs it back into our new energy equation. He replaces 2 Tauser.
And when he does that, Something important goes missing from the final formula.
Gravity.
Yeah, gravitational constant, big G, it isn't there.
Hmm.
The formula depends on time, density, and these electromagnetic vacuum constants.
Which is wild. It suggests that the energy of the Big Bang, or maybe the Light Bang, was driven by the electromagnetic properties of space itself, not by gravity.
So we have a swelling ball of light energy. But light isn't just bright, it's also heat. It has pressure.
It absolutely does. And that brings us to the thermodynamics of this whole thing. If the universe is filled with nothing but light, it behaves like a photon gas.
A photon gas. It sounds like something from science fiction.
But it's a standard concept. An area filled with radiation acts like a black body, and there are very strict rules for how its energy relates to its temperature.
So as this ball of light gets bigger, it gets cooler.
It does, but the relationship is incredibly sensitive. The paper shows that energy is proportional to temperature to the fourth power.
The fourth power. So if you double the temperature, the energy goes up 16 times.
Exactly. It's a steep curve. The paper even links this to the number of photons in the universe. But this brings up a huge, huge problem, a potential fatal flaw.
I think I see where you're going. We have this ball of light. It's incredibly dense. It has massive energy, which means it has gravity.
A lot of gravity.
So why didn't it just collapse into a black hole instantly? Why a big bang and not a big crunch 1 nanosecond later?
That is the stability check. It is the make or break moment for this theory. You have gravity pulling everything inward, trying to crush it.
But light pushes back.
Light pushes back. Radiation pressure, like a solar sail. But imagine that pressure from the entire energy of the universe. It's immense.
So for the universe to survive, the outward push from the light had to be stronger than the inward pull of gravity.
And the author calculates the exact condition for that to happen. It's a temperature threshold. The baby universe had to be above a certain minimum temperature for the radiation pressure to win and drive the expansion.
I love that because it's falsifiable. It's not just a nice idea, it's a math problem. If the conditions don't fit that inequality, the model's dead.
Exactly. Gives the whole thing teeth.
Okay, so we've got a stable, expanding sphere of light. It's all very neat. And then, just when I thought I had it, the paper throws a complete curveball. The light beam hypothesis.
Oh, this is the part that really gets the imagination going. The author just sort of pauses and asks, why are we so sure the universe is a sphere?
Well, because everything in space is a sphere, right? Stars, planets.
Sure, matter clumps into spheres because of gravity. But this is light. Light travels in rays, in beams.
So he's suggesting the universe might not be a bubble expanding in all directions, but a beam, a pulse of light.
This introduces what we call anisotropy.
Which is a fancy word for direction matters.
It is. A sphere is isotropic. It looks the same from every angle. A beam is anisotropic. It has a clear direction, a front and a back.
And if the universe started as a beam, the whole geometry changes. The math changes.
Drastically. You're not calculating the volume of a sphere anymore. You're calculating the volume of a cylinder. And the energy evolves according to a different power law.
That paints such a strange picture. Not a firework going off everywhere at once, but a directed shot of energy fired from somewhere.
It's a very different origin story.
We're definitely coming back to that idea because a directed universe is a bit unsettling. But first, let's see how this model actually stacks up against the standard one. Time for the showdown.
The tale of the tape. Light origin versus Planck scale.
The paper has a great comparison table. Let's start with energy density. How much energy is packed into a cubic meter at the very beginning?
Okay, so in the standard Planck model, the one with the singularity, the density is estimated at 10 to the 113 joules per cubic meter.
10 to the 113.
That number is just, it's meaningless.
It's a 1 with 113 zeros. There aren't that many particles in the whole observable universe.
Right. It's effectively infinite. It's the definition of physics is broken.
Okay, now for the light origin model. What's the density there?
It's around 10 to the 36 joules per cubic meter.
Which is still a gargantuan number. It's enormous.
Yeah. It is, but it's finite. It's what you might call a moderate number in cosmology. You can write it down. You can put it in a simulation. It doesn't break your calculator.
We're trading impossible for extreme but possible. What about volume?
Planck volume is 10 to the minus 105 cubic meters, so effectively 0.
And the light model?
10 to the minus 21 cubic meters.
Still unbelievably tiny. Subatomic.
Tiny, but compared to 10 to the minus 105, it's gigantic. It's the difference between nothing and something.
And this all leads to the most important metric, right? The compactness parameter.
Yes. Chi. This is basically the how classical is it score.
And in the Planck model, where is chi?
Chi is approximately equal to 1.
And 1 is bad here.
1 is bad. It means you're in the quantum-limited regime. You are right at the edge where our physics fails.
Okay, and in the light origin model?
Chi is about 10 to the minus 7.
7 orders of magnitude smaller.
Which puts it firmly in the classical regime. And that's really the big takeaway here. This model describes a classically coherent universe.
So in plain English, we don't need to break physics to explain the Big Bang.
We might not. We don't have to invent extra dimensions or wait for a theory of everything. If you just assume the universe began as light, the numbers work out using the physics we already have. The singularity just, it vanishes.
It makes the Big Bang feel less like a magic trick and more like a physical event, a thermal event.
It demystifies the origin.
So to recap this whole deep dive, we started with a singularity, a mathematical dead end. We looked at Kankha's proposal to swap mass for energy density and volume.
We saw how that connects everything to the electromagnetic constants of the vacuum, effectively replacing gravity with light as the main driver.
Then we checked the thermodynamics to make sure the whole thing didn't just collapse on itself.
And we compared the numbers, showing this model keeps us in the safe, calculable world of classical physics.
It is a really beautiful, elegant theory. But I want to leave everyone with that one lingering thought, that light beam.
The cylinder versus the sphere.
Exactly. I think most of us are comfortable with the idea of being inside an expanding bubble. It's lonely,
Right.
but it's symmetrical. But the paper leaves the door open for that beam hypothesis.
The idea that the whole universe is a directed pulse of energy.
And if the universe is a beam, that means it has a vector, it's going somewhere.
It implies a trajectory. And you have to ask yourself, if it's a beam, what determined its direction?
Who pulled the trigger? And maybe even more unsettling,
Yeah.
what are we aimed at?
And that is a question that physics definitely can't answer yet, but it certainly changes how you look up at the night sky.
It really does. Are we floating or are we flying? Something to
Okay.
think about. Thanks for diving deep with us today.
Keep asking questions.
We'll catch you on the next one.